Hello everyone, and welcome to the remote training session on CMEMS biochemical products for the Baltic Sea. This session will be divided into 4 notebooks. This is the first step and hence the first notebook of the CMEMS training session on biogeochemical products. In this notebook, we will have a closer look at CMEMS products, how they are structured, what are their formats, what kind of variables they contain, how we can explore them, how we can plot them. And then we will be interested in the seasonal variations of the biogeochemical parameters in the Baltic Sea in 2016 and 2017. Before starting, I would like to give you 2 general notes on a notebook, how it works. To execute each code cell, you can hit the Run the selected cells and advance button on the top menu. You can also use the keyboard shortcut Shift-Enter. If for any reason, while you are working on the notebook, the kernel is not working anymore, in the top menu, you can click on Restart the kernel button. Then, in the top menu, you can click on Run and run all above selected cell. So first, I'm going to introduce you to the context in the Baltic Sea related to chlorophyll A and eutrophication. And then we will start the first training step on seasonal variation of the biogeochemical parameters in the Baltic Sea in 2016 and 2017, which will start by exploring the model.ntdf file content and then plot the data in various configurations. So, most marine wildlife lives in coastal areas. These regions are rich in nutrients on which phytoplankton feeds, and this creates the basis of the marine food chain. An increase in nutrient concentration may lead to a phytoplankton bloom and to a so-called eutrophication phenomenon. Eutrophication results from the excessive input of nutrients in an ecosystem and is one of the great threats to the Baltic Sea. This excess of nutrients favors the development of primary producers such as algae and cyanobacteria, which in return reduce oxygen availability when they die and decompose. In extreme cases, marine life either dies or flees the zone. And this can have a direct impact on many essential activities in the area, such as fisheries and tourism. In such a context, it is crucial to predict and monitor different indicators of the Baltic Sea health. The CMEMS products we are going to work with provide easy-to-use, relevant, and long-term information to study eutrophication. And here you can see a picture taken from space of an algal bloom in the Baltic Sea. As I was saying earlier, this training is divided into 4 steps. Each step is designed to highlight different ways of plotting parameters and constitutes its own notebook. So this notebook is dedicated to the study of the seasonal variations of the biogeochemical parameters in the Baltic Sea in 2016 and 2017. The following notebook will deal with time series of the monthly variations of the biochemical parameters. Then we will have a closer look on how to plot vertical profiles of the biogeochemical parameters. And then we will plot vertical profiles of these parameters along sections. So let's start with the seasonal variations of the biogeochemical parameters in the Baltic Sea for years 2016 and 2017. So in this notebook, the Python cells that we will execute will use the following modules: the operating system interface module, the NumPy module to carry out scientific computation, the Xarray module to open, browse, and work with NetCDF files, the Matplotlib library, which is a Python numerical plotting library, and the basemap toolkit, which we will use in our plots to create map backgrounds. And you can hit each link to find more documentation on these modules, how they work, and the functions they contain. The first thing you need to do when you create a Python code is to import all the modules and the libraries you will need. So this is how this is what the first cell is dedicated to. We import the various libraries that we have listed here, and we give some short name to some of them. So in the following cells, when we will need to call a function from the Xarray library, for example, we will call it as xr.functionCall. So let's run our first cell in order to import all the useful libraries. So let's hit the Run the selected cells and advance button. So as you saw, when the kernel is working, there is a star here, and then when the cell is done running, a number is appearing next to the cell. So here, all the libraries have been properly imported into our environment. So now let's explore the model NetCDF file content. So in this notebook, we are going to work with the monthly mean dataset of the reanalysis products over the Baltic Sea. It means that all the variables studied in this training session are monthly averages. So this product is called the Baltic Sea Reanalysis Bio 003012. By hitting this link, will redirect you to the documentation page of the product. The spatial extent of this product span from 9 degrees to 31 degrees east in longitude and to 53.2 to 66.2 degrees north in latitude. The temporal resolution is monthly mean, so one value per month, and the horizontal resolution is 4 kilometers. These products are available from January 1993 to December 2018. The products we are going to work with were downloaded through the CMEMS subseller interface. So first, we are going to check the content of the monthly mean of the Baltic Reanalysis Biogeochemical product. For this, we need to define the root path, the path pointing to the data directory, and the file name, the path of the netmedia file, root path plus file name. Here, the root path will be data model. All the products we are going to work with are stored in the directory data model. And here we are going to work with this product, which contains a set of biogeochemical parameters on one depth, so at the surface, for the years 2016 and 2017. Okay, so root path data model, file name is root path plus the file name we are going to work with. So let's execute this cell, the cell 1.1, with the shortcut Shift Enter. So now we have told Jupyter which data we are going to work with and where it is. Now, if we want to explore a little bit more, we need to open this data. This is the purpose of cell 1.2, which uses the open dataset function of the X-array library. Remember, we called the X-array library XR. So here we are going to open the file sname. Let's run this cell. So you can see that the open dataset function from the X-array library allows to interactively browse the content of the file. First, you can check the dimension of the file. 1 depth, 523 latitudes, 383 longitudes, 24 time frames. You can also check the coordinates within the product and the core of the product, the data variables. Those are the indicators that we want to monitor over time. So you can see, for example, the mole concentration of dissolved molecular oxygen in seawater in millimole per meter cube. There is nitrate concentration, the phosphate concentration, the chlorophyll A concentration, the ammonium concentration, and the seafloor dissolved oxygen concentration. As you have maybe noticed, you can expand some information about a variable by clicking on the Show Hide Attribute button. And you can access the data representation of a variable by clicking on the Show Hide Data Rep button here. So we have just seen how to open and explore a CMEMS product. Now, what if we want to store the content of a CMEMS product into a X-array dataset? We just need to give a name to the dataset we have just opened, and then we will display its information. So let's run the cell with the shortcut Shift-Enter. So we have opened the dataset, stored this X-array dataset into FIN, and we have printed general information about the dataset. So basically, what you can see here is the information that we have seen in a more interactive way in the precedent cell. So you can find again the dimensions, the coordinates, and the data variables. Also, there are some other global attributes, like the CMEMS product ID, the deepest depth, and the shallowest depth. Here we are, as we downloaded the data only for one depth level at the surface, we are working with the shallowest depth. So just to give you a little bit more information about the NetCDF file format, for those of you who aren't familiar with it, it's a common way of storing scientific data. It contains the dimension of the data. So here, as we saw, time, depth, latitude, and longitude. It contains several variables of interest, the core of the file, which depend on one or more of these dimensions. And it contains general information about the product, like the CMEMS product ID, but also the spatial extent of the product. And you can access these quantities with the cell 1.4, where we're going to print the value of the attribute from original file easternmost longitude. And you can do the same for all other attributes. Okay. So the dataset FIN has several other attributes. If you want to print only the variables inside the NetCDF file, use the DataVars attributes. So this prints you a subset of all information available here. So you find again the variables O2, NO3, CHL. Now, if you want to print the coordinates in a product, use the coords attribute of the X-array dataset FIN. Displays you the coordinate. So, as you can see now, the dataset is 4D in latitude, longitude, depth, and time. Even if there's only one, we only downloaded the data for one depth variable, one depth level for this product. The shallowest depth, as I was telling you, 1.5 meters. If you want to print the dimensions of an ATDF file, use the dims attribute of the X-array dataset fin. You can see the dimension. 24 time frames, 1 depth, and the dimension in latitude and in longitude. Now, if you want to display the values of a particular variable or coordinate dimension, you can do it through cell 1.8. So basically it's fin.variable.values. And so here you can see the 24 dates that are available within our product. So all months for years 2016 and 2017. If you want to store these values inside an array, you can just use myArray equals fin.variable.values. So let's run an example in cell 1.9. So cell 1.9 store the value, the array, into var time. But let's be sure of this. If you want to display the value of a variable, just use the print function. So let's print what's inside var time. You can see that we find the 24 dates in var time. And just before we start playing with the variables, we'd just like to introduce you to a last way of displaying available information inside an ATDF file. You can use the ncdump-h command. This command is a Linux command. And to call a Linux command within a notebook, you just have to insert an exclamation point at the beginning of the command line. Let's execute the cell. So here you can see that this command displays you the information from the ATDF file. You can find again our dimension here, the name of an ATDF file, and the variables inside the product with the dimension that depend on the standard name, the long name, units. And the global attributes again. A difference worth to be noted is that in the reanalysis product over the Baltic Sea, the command line ncdump shows that the time variable is stored as days since January 1st, 1950. Whereas with X-array, you can X-array interprets this unit directly as a human readable date, which is more convenient. Okay, so this first part was just to give you some tools on how to open, explore, and browse an ATDF file, and more particularly a Siemens biogeochemical product. Now we are going to play around with the data inside those .NetDF files. In this notebook, we will have a closer look at the chlorophyll and oxygen monthly mean variables. So we need to define var name, the name of the variable of interest in the NetDF file. Pass out the directory to store the plots that we are going to generate during this training session. And we also need to define the mean and max value of the plot color scale. Of course, all the setup variables defined in this training session can be modified later on during your own working session and for your own study goals. So in this section, two different setups are offered. One specific to chlorophyll and one specific to oxygen. In these videos, we are only going to work with the chlorophyll variable. But when you're practicing, feel free to try the oxygen setup as well. So here you can see that we're just redefining the root path, which is the exact same root path as earlier. We are redefining the file name, which is the same as earlier. If we are doing it again here, it's just if you want to use this notebook again later on, you can directly jump to this cell to start the notebook and do the plot. You don't have to execute all the precedent cells, which are just to explore the product. So we are opening the file again, and we say that we want to work with the CHL variable, the chlorophyll variable, which remember is defined as CHL in the product here. Then we create the output directories to save the plot, which will be called plots model CHL. Mean value will be 0 milligram per metr cube, max value 20 milligrams per metr cube. So let's run this cell. So the cell printed that the plot folder was created. Let's just check it for sure. Here you can see that a few seconds ago, plots model CHL directory was created. It's empty for now because we haven't generated any figure. I am not going to run this cell because it's specific to oxygen. As I said earlier, you can run it later when you practice. So now we are going to open and store the 5 variables of interest. So in order to plot the variables of interest, we will need the time coordinate, but also the latitude and longitude coordinates, and the CHL or O2 variable. In this video, we will be working with the CHL variable. We already stored the time coordinates in var time in cell 1.9 to just play around and explore the NetDF file. We are doing it again in the following cell. The same way, we store the value, we store the longitude and latitude variable in long and lat array. To get the CHL variable from fin X-array dataset, we will use the fin var name line, and then we will display the result. So you can see that in the var X-array dataset, only a CHL variable has been kept. All other variables have been discarded. The dimensions remain the same. So now that we have decided with which quantities we are going to work, we will generate, show, and save plots in order to display the content of the cmems biogeochemical product for chlorophyll. We're going to explore 3 different kinds of maps. Maps at 2 selected dates, maps of a regional selection of data, and maps of the data for all the time frames available within the file, so for 24 dates. Let's start with maps at given dates. We will plot the chlorophyll A concentration at the surface in the Baltic Sea for March 2016 and July 2016. You can, of course, try to plot different dates after the exercise if you wish to. First, let's prepare the data to be plotted. We define the plotting window, so the corners of the plotting window. We define the dates that we want to plot, March 2016 and July 2016. And then from the X-array var dataset, which only contains the chlorophyll variable, we will select with the cell function the date plot 1, so March 2016, and date plot 2, July 2016. And we'll select the nearest date from date plot 1 and date plot 2 in the file. And then this will result in 2 X-array datasets, var date 1 and var date 2, each containing the chlorophyll concentration in the Baltic Sea for a single date. Let's run the cell. So you can see that var date 1, which is printed here, contains the chlorophyll variable on 1 depth and the latitude and longitude dimensions. The time has been removed from the dimension chlorophyll depends on, as there is only 1 time frame left in the product. Here, March, and for var date 2, July. So as we saw earlier, the open dataset function from the X-array library interprets the time variable as a date. The precision of this date is nanosecond and is too high as we are looking at monthly average values. It would be more practical to work with date objects of the type year, month, date. To do so, we can use the asType function, which allows us to define the units of a date. Here we will use the day time unit, but there are other available units like years, months, minutes. So we are going to create the date1 variable, which is the time variable inside the X-array dataset var date1, but reduced to the day time unit. And we are going to apply this process to July 2016 as well. So you can see that the time variable in var date1 has a nanosecond precision, whereas the date1 variable is only a date of type year, month, day. So once the data to be plotted are ready, we're going to explore two different ways of plotting it. One figure per date and one figure with one subplot per date. So basically one figure with two smaller figures inside the main figure. Let's start with option 1. Plot the data with one figure per date. So I'm going here to present the main functions that we are going to use to plot the data. These functions will be the same throughout this whole notebook, but also throughout the whole biogeochemical session. We're going to use the figure function that creates a new figure of dimensions, width, height in inches. That's the first function we use, just to create the figure, an empty figure. We're going to use the basemap function, which creates a map background and allows to define all the properties. So basemap, which creates the map background, can define the projection, the plotting window, the resolution. And we can add features such as coastlines, countries, we can fill the continents, we can add parallels and meridians. Then we are going to use the mesh grid function, which creates two grids of dimension long lat and duplicates the long vector along the lat vector and stores it in longi, and duplicates the lat vector along the long vector and stores it in latg. So mesh grid transforms two vectors into a grid. Then from this grid, we will convert the lat long projection to x and y axis. We will then use the p color mesh function, which creates a pseudo-color plot with a rectangular grid. So here we will plot var date 1, so the chlorophyll concentration in the Baltic Sea in March 2016, for the first and only depth level, and all the latitude and all the longitude. And we will display the results between the minimum value, which is 0 milligram per meter cube, and the max value, which is 20 milligrams per meter cube, that we have defined at the beginning of the training session. And then we will use ISType to change the datetime64 object date type. This will display the color bar that we have defined here. This will give a title to our figure with var name and date 1, and we display the title. These are the settings for the X label and Y label. And this block is to save the file into passout, which we have created earlier, and give a name to the image to be saved. And this allows to show the plot. And then we apply the exact same logic for the second plot, except that we are plotting var date 2, and that the name of the generated figures are different. Let's execute the cell. So figure 1 has been saved. You can see it through the print function here in the plot model CHL directory that we have created earlier, and it's called plot CHL March 16, 2016. So you can see that in March 2016, in the Baltic Sea, not much chlorophyll is present. But in July 2016, there is an algal bloom occurring in the Baltic Sea. And let's just check that our figures have been properly saved. If you go in plot model CHL, our two figures have been saved. Now let's try option 2. Plot the data on one figure with one subplot per date. This time, rather than using the figure function, we're going to use the subplots function to create one figure with several subplots in them. So here there will be one line, two columns. So two subplots that are going to be ordered in one line, two columns. A subplot is called an axe in Python, and each axe properties can be defined independently. So the logic and the function used then to create each subplot is the same as earlier. Thus, how the figures are displayed are different. So let's run the cell. And here we have defined each axe properly, x1 for March 2016 and x2 for July 2016 independently. So you can see one figure with one subplot for March 2016 on the left and one subplot for July 2016 on the right. So, as I was saying earlier, between March and July 2016, the CHL-A concentration increased significantly in the Gulf of Riga compared to other areas in the Baltic Sea. So let's take a closer look to the Gulf of Riga. So we are going to explore how to perform a regional zoom and the comparison of several dates. So first, we are defining a reduced plot window. And here we define the latitude, min, and max that we want to extract from the product. To extract this latitude and longitude, we will use again the cell function. And we will extract a slice of latitude between lat-min and lat-max for the Gulf of Riga. Same for the longitude. Then we will store the selected latitude and longitude into lat cell and long cell. And we do it for both dates. And we're working on var date 1, which contains the chlorophyll variable for March 2016, and var date 2, which contains the chlorophyll variable for July 2016. Let's run the cell. And now we are going to plot the data on one figure with one subplot per date. So this is the exact same logic as earlier, except that we are working on a reduced dataset with long cell and lat cell. So let's run the cell. So you can see here that we have zoomed in on the Gulf of Riga. And this highlights the differences in CHC and chlorophyll concentration in this area between March and July 2016. And then last figures for this notebook, we're going to plot the monthly variations of chlorophyll concentration in the Baltic Sea over 2 years. So we're going to work with the 24 time variables. So we define the plot window again, which is we are back to the whole Baltic Sea. We create a figure with 24 subplots that are organized in 6 lines and 4 columns. We convert the axis to a flattened 1D array to be able to loop over them. And to create all figures, we loop over the time values. So each time frame will be plotted on one axis. Okay, and so we use the same settings for each axis, except that in the P color mesh, we are working on a var dataset which contains the chlorophyll concentration in the Baltic Sea for all time frames. And so we plot the particular time frame Ti. Let's execute the cell. So it's looping over all 24 time frames available in the project. So every month in 2016 and 2017. So you can see that we just plotted the chlorophyll A concentration for every month, so the average value over each month in 2016 and 2017. And this plot clearly highlights where and when the most harmful algal blooms occur. So these algal blooms primarily occur in coastal areas where there is the most excess of input nutrients, and it occurs during the summer months where there is the most sunlight, and it spans from April to August. In the next step, we are going to investigate how these algal blooms are correlated with other parameters. So as I said at the beginning of this video, we worked with the chlorophyll variable, but if you want to repeat the exercises with the oxygen concentration or other variables that are available in the product, can jump to var-B. Now let's go to the second step of the tutorial.